Datasets in real-world applications can have numerous features, making it really difficult to analyze and also visualize the data, especially for the large neural network architectures, which are prevalent in many domains, can have millions or even billions of parameters. So that's why we want to introduce dimensionality reduction techniques, such as linear discriminant analysis, can help to mitigate these issues by finding a lower dimensional representation of the data that preserve the important information. Ronald Elmer Fisher bring up this Fisher discriminant analysis idea in 1936. This method has been existing for almost a century, but it still have a limitation that only can obtaining a number of lower dimensional directions, that is, one less than the number of classes. So that's why we want to propose this method called Generalized Optimal LDA, shortened as GoLDA, to address the problem that has been ignored in the literature for almost 100 years. So for the classical LDA, the way to solving it is to solve a generalized eigenvalue problems. But for our method, we try to maximize the Fisher ratio by adding another constraint that each of the discriminant directions has to be orthogonal to the previous ones. And after that, we can obtain these bottom equations, which is a recursively way to solving the different discriminant directions by using the different generalized eigenvalue problems to make sure those directions has to be orthogonal to the previous ones and also maximize the Fisher ratios. Now let's move on to these bottom images, see how the GoLDA actually work. So first, we can have this first eigenvector, which is shared by the two different methods. And this three class is separate in these directions really well. And now let's move on to the second eigenvector obtained by the classical LDA. There's two class overlapped on top of these directions. If we move on to the GoLDA on the second directions, it still have the separability to separate these three classes really well, because the aiming is to maximize the Fisher ratio. It's not just to solving the generalized eigenvalue problems. On the right-hand side, first thing I want to show you is how the Fisher ratio change when we change in the different directions. So here is a 10 class problems. If we're using LDA, want to obtain more than 10 directions, we can see the Fisher ratio just drop to 0. But if we want to use GoLDA to obtain, they don't have the limitation of can only obtain one less than the number of classes, and also the Fisher ratio doesn't drop dramatically at the beginning. And the above three images want to show you how this method working on the classification problems. So here is a three class problems. On the first direction, it can separate these three class really well. And when we move on to the third directions by using LDA, we can see these three classes all overlapped. There's no discriminant information at all. But if even though when we move to 8th direction by using GoLDA, it still can push one class out. There's still some information that we can use for the classification problems. Thank you.